So today we will discuss about Euler Totient function. So it is denoted by phi of n, where n is a natural number. So let us define this at first. Phi n is defined by the number of integers inside 1 and n, which is co-prime to n. So formally k is inside 1 and n such that GCD of k comma n is 1. So if you want to know what phi n is exactly in terms of n, so there are a lot of proofs, but so phi n is n times product p divides n 1 minus 1 by p. So most of us know this maybe. So today I will give you some probabilistic proof of this fact. So let's say, so the probability of a randomly chosen number between 1 and n is co-prime. What is the probability of that? This is phi n by n, right? Co-prime to n, less than equal to n is phi n by n. And what is the probability of a randomly chosen number is divisible by p? It is 1 by p, right? And then what is the probability of randomly chosen number is not divisible by p? Is 1 minus 1 by p. So by definition of phi n, every number you choose between 1 and n which has GCD 1 with n, co-prime to n, that means it is not divisible by any prime factor of n. So what is the probability of that? So a number is not divisible by any prime factors of n. The probability of that is 1 minus 1 by p. But we are looking at all the prime factors of n. So that means we have to take the product p divides n 1 minus 1 by p. Right? So phi n by n equal to p divides n 1 minus 1 by p. So phi n equal to n times product p divides n 1 minus 1 by p. This is something nice. So we are interested in some interesting properties of phi n. So phi n times n prime equal to phi n times phi n prime when GCD of n comma n prime is 1. That means they are co-prime. And second property is phi of p to the power a equal to p to the power a minus 1 times p minus 1. So just plug in the formula n equal to p to the power a. So there is a nice sum. We want to look at sum d divides n phi of d. Okay. So is there any nice closed form to this? So we can look at the following product. The following product p divides n 1 plus phi p plus phi p squared plus dot phi p to the power ap. So where ap is the largest power of p that divides n, largest power of p such that p to the power that power divides n. So where n is p to the power a p1 to the power ap1, p to the power ap2 up to pk to the power apk. This is well-known prime factorization of a number. So let us just compute it, because we know the value of phi at p to the power some power, any power. So by multiplicative property of phi, I want you to think that this product, if you compute this product, this exactly gives you some summation over d divides n phi of d. So summation over d divides n phi of d is exactly the sum, is exactly a, if I just named it. So let us just compute the product. So product p divides n 1 plus p minus 1 plus p times p minus 1 plus p squared times p minus 1 dot p to the power ap minus 1 times p minus 1. So which is product p divides n 1 plus, take p minus 1 outside, this is a geometric sum, and just cancel p minus 1. So we have product p divides n p to the power ap, which is n by definition. So summation d divides n phi of d is n. So this result is due to Gauss, and this is a very nice formula. Okay. So I want to möbius. So I want to say some connection of this Euler Totient function with möbius function. So let us just define the möbius function. It takes 1 when n equal to 1 and minus 1 power k when n is a product of k distinct prime factors, and 0 when n is not square free. That means n is divisible by some square of a prime number. So there is a möbius inversion theorem. The inversion theorem. So if we have two arithmetic functions, f and g, and gn is sum of d divides n, f of d, then we have f of n is summation d divides n mu of d, the möbius function of d, times g of n by d. This is a very interesting theorem. So we want to apply this. So using this, as we have, using this we have as sum over d divides n phi of d is n, divided phi of d is n, that will imply that phi of n equal to some d divides n mu of d times n by d. Okay. So you can write it as phi of n equal to some d divides n d times mu of n by d. Because d divides n, so you can replace d by n by d. So now we will prove some we will prove an interesting formula for phi n, and which is phi n equal to some k from 1 to n GCD of k comma n e to the power 2 pi I k by n, and the real part of this guy is cos 2 pi k by n. Yeah, so actually I will prove that phi n equal to summation k from 1 to n GCD of k comma n times e to the power 2 pi I k by n. Okay. Yeah. So for proving it, we have to define something called NQ. So NQ is sum of all qth roots of unity. Formally, this is k from 1 to q e to the power 2 pi I k by q. Sorry, I k by q. And we know that when q equal to 1, nq is 1. Oops. nq is 1 when q equal to 1, and nq is 0 if q is greater than 1. Yeah. And define CQ, the Ramanujan sum, the sum of all primitive qth roots of unity. Formally, sum over k in between 1 and q, k comma q is 1 e to the power 2 pi I k by q. So there is a relation between NQ and CQ. So just think about it. By grouping, we can write NQ as sum d divides n or d divides q C of d. Okay. Because in NQ we are summing over all k's up to q, and in CQ we are summing over all primitive k's, right? So now again by Möbius inversion, CQ is some d divides n or d divides q mu of q by d times n of d. Nice. And we know that n of 1 is 1 and otherwise it is 0. So it only survives when d equal to 1 and otherwise this is 0. So CQ is mu q. That means CQ is actually the Möbius function itself. Yeah. So as we noticed earlier that we noticed earlier that the formula for phi n is phi n d divides n d times mu of n by d. Okay, which is equal to d times, just replace c of n by d. Just replace d times c of n by d, as we showed the CQ is mu q, and which is d divides n d times, by the definition of c of n by d, j comma n by d is 1 e to the power 2 pi I j by n by d. Okay. So now just define j prime equal to j times d. define j prime equal to j times t. So then we can rewrite the sum as d divides n, sum over j prime comma n is d e to the power 2 pi I j prime over n, right? Yeah. And yeah, if you can think of this sum is exactly what we want. So again, by grouping, we can rewrite this sum as sum k from 1 to n GCD of k comma n e to the power 2 pi I k by n. Yeah, just think about it, because define d equal to GCD of some k comma n and group the terms when the GCD is d. Yeah, grouping the elements from 1 to n which has GCD d with n. So then you can get the equality. So as phi n is real and phi n belongs to natural number, we want to look at the real part of the left hand side. So the real part of the left hand side is k from 1 to n GCD of k comma n cos 2 pi k by n. 2 pi k by n. Yeah, so this is a very nice formula. Yeah, then you can start. Yeah, a very special series. A special series about this torsion function. So so we are interested in, we want to look at sum over n from 1 to infinity phi of n times x to the power n by 1 minus x to the power n going to 1 to infinity. Yeah, obviously for mod of x strictly less than 1. So I want to know, is there any closed form of this sum out of this series? So yeah, for mod x less than 1. Yeah, so look at a single term of this series. There is the n term, this is phi n times x to the power n divided by 1 minus x to the power n. So as mod x is strictly less than 1, you can write x to the power n by 1 minus x to the power n as this, in this fashion. So x to the power n plus x to the power 2n plus x to the power 3n up to infinity. So if we sum up over all n's, right? So if you sum up over all n's, so we want to know what is the coefficient of x to the power k for any k. So the coefficient of x to the power k appears when a number divides k, right? Because think about it, the coefficient of x to the power k is sum d divides k phi d. Yeah, because if d divides k, then phi d times the series. So somewhere in the series x to the power k will appear. So that's why sum d divides k phi d is the coefficient of x to the power k. Yeah, if d divides k equal to d times d prime, then phi d prime appears with x to the power d times d prime. Okay, so that's why this is a sum over d divides k phi of d. So now, as we know that sum d divides k phi of d is k. We proved earlier. So the left hand side is, so right hand side is sum over k from 1 to infinity k times x to the power k, which is x by 1 minus x whole squared. It's a very nice formula. So that means sum over phi n times x to the power n divided by 1 minus x to the power n from 1 to infinity is x by 1 minus x squared. So I can tell you the in general what is happening. So n from 1 to infinity phi n times x to the power n by 1 minus x to the power n is k from 1 to infinity d divides k phi of d times x to the power k for any arithmetic function fn. So if you can choose fn to be the trivial function, I mean 1, then we have, if you define fn is 1, then then we have sum n from 1 to infinity x to the power n by 1 minus x to the power n is sum k from 1 to infinity sum over d divides k of the identity function x to the power k. And this is number of divisors of k, is dk. K from 1 to infinity dk times x to the power k. So this is the general fact. Okay. Now connection of Euler Totient function to zeta function. So so let us consider the sum n from 1 to infinity zeta of n by n to the power s. As we noticed earlier that phi n is multiplicative, so phi mn equal to phi m times phi n when GCD of m comma n is 1. So then if we look at the following product, so if you look at the following product P, product over prime numbers, one plus phi p divided by p to the power s plus phi p squared divided by p to the power 2s plus dot dot dot. So think about it. If you evaluate this product, you will get this sum because phi n is multiplicative. So this is exactly equal to product over p 1 plus this guy. So what is phi p is p minus 1. What is phi p square is p minus 1 times p over p to the power p to the power 2s plus dot dot dot. Means phi p cube is p minus 1 times p squared. So product over p 1 plus p minus 1 times 1 by p to the power s plus p by p to the power 2s plus p squared by p to the power 3s and so on. So now which is product over p 1 plus p minus 1 by p p1 by p to the power s minus 1 by 1 minus 1 by p to the power s minus 1. Just a geometric series, right? So which is product over p1 plus p to the power p minus 1 by p 1 by p to the power s minus 1 minus 1. So now by doing some algebra, we have product over p 1 plus p minus 1 divided by p to the power s minus p. And again, this is product over p to the power s minus 1 divided by p to the power s minus p, which is 1 minus 1 by p to the power s divided by 1 minus 1 by p to the power s minus 1, and which is zeta of s minus 1 divided by zeta s, if you know the Euler factorization of zeta function. So this is a nice relation to zeta function. So sum over phi n by n to the power s is zeta s minus 1 divided by zeta s. Yeah, so these are the nice formulas about Euler Totient function. So there are many more, but yeah, at least these are nice. Okay, so yeah, thanks for watching.